So for today's session, you have joined with your microphones on mute, and that's by design. Questions and answers will be taking place after the talk. However, if you have any questions about any topics or any content that Professor Advincula brings up today, please send them in with the questions with the chat module on your control panel when you logged into the session. And then after the talk, we'll dedicate maybe 5-10 minutes to answering them sequentially. If you have any further questions that weren't addressed at the end of the session, you remember anything afterwards, we will also be giving our email addresses and the Park Systems website, and also the location of where all these video recordings are archived. All of our webinars are recorded and archived for future watches. So let me go ahead and turn things over to Professor Advincula, and let's get started. Professor?
Okay, so let me fix some things here. Sorry, apologize for this. Okay, so let me go and apologize. I had to repurpose some of the slides. So I'm with Case Western Reserve University, and first of all, I'd like to thank Gerald for the opportunity to give this webinar as his host. But of course, Park AFM for being the host for today's webinar. Let me remind you that in November we have another webinar, and that will be quite relevant and somewhat contemporary to the recent Nobel Prize win in supramolecular chemistry. But today we will focus on Dendrimers for AFM. And I'm using a more recent presentation I did at the Polymer Society meeting of Korea, meeting recently in Jeju Island. So first of all, Case Western Reserve University, we are located in Cleveland, Ohio at the University Circle, together with the Cleveland Museum of Art, Cleveland Orchestra, Cleveland Clinic, easily a cultural center in the heart of Ohio. We are located at the Kent Hill Smith Building. My home department is the Department of Macromolecular Science Engineering. This is where we are located, and my office is at the 5th floor. Now, a lot of things we do relates to surfaces, investigation of different types of analytical methods, chemical interfaces, surfaces, nanostructure as well. And on the other hand, we are interested with polymer materials that have conjugated pi-conjugated systems that can undergo electron transfer, pi-electron delocalization, charge carrier generation, which makes it useful for a variety of devices such as light-emitting diodes, sensors, actuators, and solar cells. So the type of chemistry we do, to this respect, makes us interested in making new pi-conjugated polymers, which can include polyfluorines, polycarbazoles, polythiophene, polyphenylene, vinylene derivatives. In this case, these are electroactive materials that are capable of fluorescence, charge transport, electron transport, and so on. And part of our interest is mainly in looking at dendrimeric systems that are derivatives of, let's say, thiophene or carbazole. So the talk today largely centers on dendrimeric materials and how we've used atomic force microscopy to characterize these systems. So first of all, let me introduce what a dendrimer is. A dendrimer basically is a topologically exact hyperbranched molecule or macromolecule. Whereas we know most polymers to be linear, dendrimers are indeed large molecules, except that their topology or their exponential growth in terms of their peripheral group can actually be programmed or can be synthesized by two approaches. One is called a convergent approach, and the other is a divergent approach. A divergent approach means that the dendrimer or the branches grow from a central core. On the other hand, a convergent approach means you grow the branches and then you put them together. But what makes dendrimers unique is that they have functional groups which can be built in the core or part of the peripheral group or be present on all the whole dendrimer. And also by generational growth, you can have generation 1, 2, and 3. You can enlarge the dendrimers and grow the peripheral group, for example, in an exponential manner. In some cases, the core itself is of high interest, but also the cavity within the core. Hence, dendrimers have been often used for drug delivery, catalysis, different types of chemical sensors, and so on, mainly because of these controlled properties and generational growth. Now, I'm going to talk today as well about nanoparticles, simply because we have specialized through the years the combination of hybrid materials that is of dendron ligands and nanoparticles as core. In this case, I'm showing you an example of a chalcogenide nanocrystal of cadmium selenide, in which the quantum size effect is very well known, where you change the size of the nanoparticle and the fluorescence or emission changes as a function of size. There are advantages in terms of nanoparticles in terms of surface to volume ratio, but at the same time these are interesting nanomaterials that not only show energy transfer but charge transfer capabilities. One thing that we have also looked at is the use of different types of ligands. In this case, gold nanoparticles, when initially synthesized, can be capped with polymers or surfactants that tend to stabilize their size and shape and then enable them to be investigated as individual particles. Here, on the other hand, we can see that gold nanoparticles can actually be mediated or be used as markers where the fluorescence can be effectively quenched based on the distance between the gold nanoparticle and the fluorophore. And this, as we'll talk later, has to do with the energy overlap between the absorption band, plasmon band, and the fluorescence of a dye, which can result in selective quenching as a function of size. So I'm going to talk about several dendrimeric systems, and then each one of these will be evident how we've used AFM effectively to characterize their morphologies. First, I'm going to talk to you about conjugated typing dendron polymer materials. So we have synthesized, in this case, polythiophene dendrons or dendrimers using a convergent approach through metal-mediated reactions such as Kamada coupling, Stille coupling, or as you can see here, we can utilize a AB2 monomer, which is a basic unit for dendrimer synthesis, where the thiophene has two bromo groups, alpha beta, and then you have a hydrogen group, proton group, which makes it susceptible for lithiation reactions. So with this design, we can then grow the dendrimer by basically growing branches of, let's say, 3T. Using thin tributyl initiator, we can then couple this to react with another dibromothiophene to produce 7T, and then repeat this process with dibromothiophene to grow 15T. So easily we can see here 1 generation, 2 generation, 3 generation of dendrons, which we can then assemble to larger dendrimers as such. So if we take, let's say, this tetrafunctional bromo derivative, we can then couple 3 thiophenes to produce this 14T derivative, or we can take the 7T to come up with this 30T derivative. Now what's interesting here is that although we've observed most of the energy harvesting properties as well as their ability to shift the absorption. What's interesting is by AFM, we observed that these dendrimers are capable of forming two-dimensionally packed, hexagonally packed structures as shown here. In this case, we've used AFM to observe this two-dimensional crystallization on a graphite surface where the polymers are parallel side packed on the surface. On the other hand, in cases where we have utilized solvents, selective solvents, they actually pack in columnar bases to form this type of nanowires. So here you can see that AFM offers a direct visualization of the supramolecular assembly of these dendrimers to form these structures on flat surfaces such as mica or graphite. We have since then prepared different types of polytyphene dendrimers with different core groups. In this case, a ruthenium complex with phenandrolene derivatives or bispyridine. Here we can see a complex of ruthenium forming a 3BP derivative as shown in this schematic diagram. So you first synthesize the dendrons, in this case the ligand, which then can be complex with ruthenium, resulting in structures like this. And what's interesting is that we can have a full dendron, a dendrimer, or a half dendrimer. In this case, we can complex it with these two groups already present to come up with various structures which then becomes evident in terms of their reduction oxidation state, which we observe by CV, to differentiate between these different types of ligand packing. On the other hand, we can control the absorbance as well as the fluorescence shifts based on the concentration and the type of ligand we observe, showing different types of packing behavior based on the aggregation as seen by this isosbectic point with different pH. Unfortunately, I will not be able to show you some of the AFM images here, except that we focus in particular with the energy transfer properties as well and their complexation as shown by this fluorescence spectra, where the self-quenching mechanism or the packing of, or stacking rather, of this polytyphene complex has resulted in quenching or relaxation of their fluorescence behavior as shown here. So this is what we call an indirect method of characterizing aggregation. We have also synthesized porphyrin cores. These porphyrin cores stack in solution as well, as shown by this shift in their aggregation, which signifies a shift from H to J aggregates. And again, indirectly, we were able to observe this by the transition in fluorescence coming from one type of aggregate to another as shown in this fluorescence spectra. Now, again, unfortunately, I will not be able to show AFM pictures here simply because we were not able to isolate it in the first place, but also what we try to highlight here is that aggregation and stacking can also be observed indirectly by looking at their energy transfer properties. Now let me then turn to a hybrid complex of a cadmium selenide nanoparticle and a dendron based on polytyphene. So to synthesize this, what we started with is the synthesis of a polytyphene dendron with a phosphonic acid side group, which can then be used to chelate with a cadmium selenide nanoparticle. So by itself, it's an interesting fluorophore, as shown with a fluorescence of around 550, absorbance up to 500 tail. And what we did is we indirectly, through substitution, functionalize it on a cadmium selenide particle. So this cadmium selenide particle, through ligand exchange reaction, was then coated with the polythiophene dendrons. And we track this complexation or ligand exchange by FTIR. But from AFM, we were able to observe directly these hybrid nanomaterials individually as shown here, and the heights confirm the size of the nanoparticles to be about 4 nanometers, inclusive of the polythiophene ligand complex. We were able to characterize their fluorescence and absorption properties. And what's interesting is that the cadmium selenide, when surrounded with the polythiophene dendrons, has a quenching mechanism, which we attributed to an electron transfer between the ligand and the nanoparticle, which is interesting because this type of behavior actually makes it useful for solid-state devices such as photovoltaic devices or the photovoltaic effect, as I'll show you soon. We noticed this when we did the photocurrent properties of these polythiophene dendrimers, in that they observe a change, we observe a change in IV curves as a function of light. So in illumination and under dark, we were able to see a current shift in behavior. And this is similar to some of the properties that can be observed from polythiophene materials. For example, way back in 2002, simply by mixing cadmium selenide and polythiophene, a photocurrent behavior was observed, enabling Alivasatis et al. To actually use this for photovoltaic devices. So in this case, we prepared a very simple device of this cadmium selenide capped with polythiophene dendrons, and we were able to observe a photocurrent behavior based on this IV curve with an aluminum cathode and ITO anode configuration. Now let me turn to another example of how we've used dendrons to cap gold nanoparticles. In this case, we were interested in the quenching mechanism of the plasmon absorbance with the dendron. And here, for example, we synthesized dendrons of different chain lengths of alkyl-thiophene spacers. So we have 2 carbons versus 11. 2 carbons versus 11, except that this is 70 and 3T. And the synthesis is basically a direct ligand functionalization of the gold chlorides versus exchange that was done in the previous example. So we use this basically as dendron ligands. So notice here that the thio group will then be capped on the gold nanoparticle surface to produce nanoparticle hybrid dendrons that look like this. So the gold nanoparticle core then should be surrounded by a finite number of the 70 or 3T derivatives with different chain lengths. In this case, TEM actually was an effective tool to look at the dispersity through this histogram, as well as the effectiveness of the direct synthesis of the gold nanoparticle hybrid dendron. But here you can see the equivalent AFM. So what's interesting here is both AFM and TEM have consistent results in terms of size. AFM actually gives us a direct height measurement, whereas the TEM gives us a histogram of the nanoparticles, and the widths can be directly measured from the image. So why are we interested in these materials? Well, the gold nanoparticle basically has an absorbance of around 550 nanometers, whereas the terthiophene and the heptathiophene have fluorescence around 500 to 550 nanometer region. So what the point is, by overlapping the absorption and the fluorescence, energy transfer mechanisms can actually be elucidated as a function of distance. So just to show you the effect, here is a terthiophene with 2 carbons. Because of the proximity or closeness of the terthiophene to the gold core nanoparticle, we can have as much as 90% quenching of the fluorescence. On the other hand, when we increase the number of carbons to 11, so it changes spacer length to 11, we were able to observe only 70% quenching. Now, in the case of the 70, where we have less overlap, we get 85% quenching and 60% quenching. So what this indicates is that the quenching mechanism is simply a function of distance from the gold nanoparticle core. So what actually happens with the gold nanoparticles is there are 4 different modes of quenching. It could be an intermolecular interaction between the dyes itself, or an energy transfer between the metal nanocore to the dye, or an electron transfer between the metal to the nanocore, or other unquenched components or even heat transfer components that are not accounted for. So this energy transfer relationship is something that hybrid dendrimers are capable of exhibiting with their corresponding inorganic nanoparticle cores. Now, we have investigated actually the use of different types of thiophene cores for electroluminescent display devices. In this case, we have these 2 dendrimers with thiophene groups, again showing their absorption and fluorescence behavior. The fluorescence for the thiophene indicating a fluorescence of around 450. And then we can actually complex this as well as copolymerize with PBK to observe a shift in electroluminescence from 550 to 600. So what it is by electrochemically cross-linking the thiophene units, we end up producing polythiophene units that show this dramatic shift in the fluorescence behavior. This was done by cyclic voltammetry. The cyclic voltammogram here indicates a clean sweep in which the oxidation at about 0.6 to 0.7 effectively converted the thiophene to polythiophene. Since we polymerized this on an ITO device, we were able to prepare the electroluminescent device or organic LED or polymer LED to show us a electroluminescence behavior as shown in this view graphs here in terms of the charge electric current density as a function of applied voltage, the efficiency of the light behavior as a function of current density, although not as efficient, but what's interesting here is by the addition of PBK, we were able to dramatically improve the efficiency versus that of the system without PBK. Now, these are basically light-emitting diode devices that are orange in color, as shown here. The exact EL spectra shows fluorescence at around, or emission at around 600. And again, the charge current density and efficiency for the crosslink system is shown here. So what I've highlighted here is that dendrimers can be utilized to prepare electroluminescent devices. Now, from thiophene, we actually investigated other types of carbazole-based electroactive monomers. In this case, utilizing, again, a convergent method, we synthesized carbazole-terminated polyether dendrimers. So by synthesizing this first route to produce your AB2 monomer, you will end up with a G1 dendron. And then after reduction of the ester, you can terminate this with an alcohol. This becomes the AB2 monomer for the generation 2 dendron. And this was actually done very efficiently using a sonication reaction. Again, by reduction of this, we are able to convert this into another AB2 type monomer to produce G2OH. So using these different dendrons, we were able to assemble dendrimers with a trifunctional core to produce your G1 dendrimer, G2 dendrimer, and then even bigger dendrimers such as G3 and G4. So these are what we call reactive or electrochemically active dendrimers that can be utilized like the tertiophene dendrimer for certain devices. Now, characterization-wise, it's interesting because you can actually track the size directly. By MALDI-TOF, we have the exact molecular weight of the generational dendrimers. And as you can see here, the molecular weight actually increases exponentially because of the exponential growth. On the other hand, GPC gives us the size by size exclusion chromatography, or the measure of the hydrodynamic volume. So G1 will be the smaller molecule giving you the higher retention volume. And as you go from G1 to G2 to G3, you're increasing the hydrodynamic volume as a function of molecular weight or size. But what's interesting here is that although G4, as seen in MALDIs, is actually much higher than G3, yet the hydrodynamic volume suggests that it's actually smaller than the purported molecular weight. So what actually is happening is that the G4 dendrimer shows a contraction in size because of the frustrated geometry. The G4 dendrimer, even though exponentially it's a bit higher molecular weight, yet the hydrodynamic volume does not linearly follow that size because of the frustration or the contraction based on this very tight structure in trying to accommodate 3 G4 dendrons in one dendrimer. And much can be said as well with the glass transition behavior as well as the thermogravimetric analysis. Again, how did we use AFM to characterize these dendrimers? Well, in this case, we prepared thin films based on the Langmuir-Blodgett deposition method. And what we observed is that when we remove these films or this assembly at various surface pressures, so from 5 to 15 to 30, we were able to see aggregates or agglomerates of these dendrimers as shown here, from pearl necklacing to spaghetti-like structures to globules. Here we see the morphology at 2 different concentrations with 3 different surface pressures, indicating that we can control the morphology of the dendrimer aggregation on a Langmuir-Blodgett film by pressure or concentration and directly observed it by AFM. Now, since these dendrimers are actually electrochemically active, and I'll explain to you in a little while why we are very particular with this reactivity, is that these carbazole units can link up together or with the neighboring carbazole units to produce polycarbazole, and this can be done electrochemically. So in this case, once we prepare films of various concentrations or packing, we can actually pattern them or use electrochemical nanopatterning, which I covered on my previous webinars using a conducting AFM tip. So in this case, we have these films prepared on an ITO substrate, and then we move the tip. In this case, it's very clear the term UH was patterned on this LB film. These are electrochemically active, as proven here by the CV diagram. But again, electro-nanopatterning can be manifested with this still electrochemically active dendrons. And we were actually interested in observing the individual cross-linking of these dendrimer units, as can be shown, as shown here. So in an intramolecular fashion, these carbazole units can link up to form this type of globular structure. We have followed this indirectly with absorbance and NMR results. But what's interesting is that AFM is an important tool for us to directly visualize this cross-linking process. So here is the image before and after. What we have here is a flat ITO substrate or a silicon, doped silicon surface where we have the dendrimers placed on a very dilute solution on the surface, and then we applied a current by rastering over the image, and we observed that the height increase, as shown here, after we have applied a bias voltage along the surface. And then we remeasured the height. We observed that the height increased as we did this electrochemical in situ cross-linking. So what we believe happened is that the dendrimers were able to polymerize intramolecularly, resulting in a more compact structure. So here is a relaxed flat structure before electropolymerization. Then after electropolymerization, it contracted to a lower hydrodynamic volume nano-object. Now let me skip this slide and instead go directly to this material. So what we have here is that we have, instead of the polythiophene that I showed earlier, we actually utilized a cadmium selenide and instead surrounded it with capping ligand of a carbazole unit. So this was prepared again by direct synthesis of the cadmium selenide, and then here the corresponding fluorescence and the absorbance. Now what's interesting here is that when we hybridize the cadmium selenide and the carbazole, we observe a decrease in fluorescence of the carbazole group, but an increase in the fluorescence of the cadmium selenide unit. So this is an indication of a charge transfer mechanism instead of an energy transfer that was observed, let's say, earlier with the gold nanoparticle. That means that this species here can have charge generation perhaps through irradiation with light or photovoltaic effect, which we did not have an opportunity to demonstrate as a device. Nevertheless, again, atomic force microscopy was vital, or one of the tools anyway, that we used to characterize the nanoparticles as we directly deposit them on the ITO surface. So this height histogram shows the corresponding diameters of the nanoparticles that were also consistent with some of our TEM imaging studies. So in principle, what we have here is essentially a cadmium selenide surrounded with carbazole dendrons, which can be electropolymerized intramolecularly or as a film can be electropolymerized intermolecularly as well as intramolecularly. So by depositing this film on an ITO substrate, we can then electrochemically polymerize the carbazole units. And what we did is after electropolymerization, after 50 cycles, we then observed the absorbance and the fluorescence. So what we observed is the shift in the absorbance up to 500 nanometers, indicating the presence of the polycarbazole units. On the other hand, the fluorescence resulted in a decreased, along the polycarbazole unit, but an increase in the or another, not increase, but retention of the cadmium selenide fluorescence as shown here, which indicates that the cadmium selenide was not changed, but the fluorescence of the carbazole upon conversion to polycarbazole shifted as compared to a drop cast film. So this is the fluorescence actually of a polycarbazole unit. Now, what's interesting is that if we compare the homo-lumo properties of the carbazole and the cadmium selenide, cross-linking of the carbazole to polycarbazole units increases the HOMO, or the highest occupied molecular orbital. Now this value here may seem insignificant based on just the fluorescence properties alone, but actually it's a very important property when it comes to the preparation of light-emitting diode devices, because this can translate to a lower turn-on voltages. Now, an interesting phenomena that we actually observe with these materials is that we can pattern them using photomasking techniques. So in this case, we simply prepared the film and then irradiated it with light at between 250 to 360 nanometers or UV region. And what happens is that we get selective patterning, in this case a PEM green, that shows that the quenching is observed between the carbazole units that were photo patterned or irradiated, indicating in our case the possible destruction of that ligand to cadmium selenide interaction based on the photochemical reaction of the phosphonate groups. That's one mechanism which probably would have resulted in change in intensity as shown here in both the blue and the green excitation contrast. So what I've shown here is that dendrimers are very interesting materials. They can be synthesized through convergent or divergent methods. They have particular ordering characteristics for supramolecular assembly, thin film strategies, and in our case, we were able to demonstrate hybrid formation with nanoparticles as well as cross-linking with an electropolymerizable unit. But at the same time, I hope you've gotten an appreciation of how powerful atomic force microscopy is when it comes to direct visualization or characterization of the dendrimers. Certainly, there's complementarity with techniques like transmission electron microscopy, but AFM, when done with the purpose or even the application of patterning methods, is a unique analytical tool for characterizing dendrimer materials. So with that, I'd like to thank you, and I will be happy to answer any questions that the audience may have.
Very good. Thank you very much, Professor, for the overview, the survey of dendrimers and also their characterization with atomic force microscopy. It's now, as the professor mentioned, it's now time to open things up to questions and answers. We do have a general question that's already in queue. So I'll also give some time for those of you who are still giving thought to digest the material that was just presented to try and distill those into questions. I'll give you a couple minutes to do that. In the meantime, before we start answering questions, as the professor mentioned at the beginning of today's session, there will be another presentation next month that he will be giving, again on supramolecular chemistry, but this time within the context of the recent announcement of the 2016 Nobel Prize in Chemistry being awarded to Sauvage and others for the work on developing molecular machines, nanomachines. So that will be next month. And again, before we end today, I'll be sending out links to both the registration page for that talk, so you can join us for that, as well as the repository, the archive, for where all of the recordings of the sessions that Professor Advincula has given over the past year are stored. All of these are all on parkafm.com, as well as Park Systems' YouTube channel. So you can always forward links to colleagues. If you're in academia, you can forward them to your students or anyone else whom you think may find them useful. We've covered many different topics with Professor Advincula and other speakers across many different applications, so I'm sure there's a webinar for just about everybody. So, with that said, the very first question is just a general question, but I think it is something that maybe a lot of people have wondered, and also something that may refresh memories for people old and also new. It's will the slides here, Professor, will they be available to participants after today so that they can further digest the information themselves?
Yes, Gerald. Yeah, selectively, the participants, if they watch the webinar today, they can email me directly at rca41@case.edu, and I will respond accordingly. So the website, I have my group website, rcapoly.net, and you can actually get more information about our group and the publications we have. But certainly, I'd be happy to correspond with our viewers directly through email.
Excellent. And as you can see here, everybody, this is Professor Advincula's research group's website. And I've also put in the professor's email address in the chat as well. That way you can take reference of that there. Okay, well, does anyone else have any questions? Again, if you have any at this time, feel free to use the chat module, the questions module, to send them in by typing them in. Before we maybe close things, if no one has questions, Professor, can you give us a little preview maybe about what the talk next month will be about?
Yeah, thank you, Gerald. Yes, the talk next month will be quite exciting because I will be focusing not only on AFM, but I'm going to have a very good introduction about supramolecular chemistry, nutty polymers, and nanomachines. As most of you might have heard, the Nobel Prize winners in chemistry for 2016, Sauvage, Fraser Stoddart, and Feringa did excellent work, and I would consider the generational leaders for supramolecular chemistry as applied to things like nanomachines, sensors, energy transfer devices, molecular harvesting devices, and so on. So you will learn a lot about chemistry, synthesis, perhaps art, nanomachines, and atomic force microscopy. So it promises to be an exciting webinar for those of you who are enthusiastic in these topics.
Very good. Again, in the chat module, I've distributed to everyone, in addition to the professor's email address, the registration link for that webinar next month. We will be doing it, instead of Thursday, we'll be doing it on Wednesday rather. It should be November 9th. And yes, please, forward this link along. Everyone is invited. And we hope to see you there. If you have any questions at all about atomic force microscopy and the solutions provided for nanocharacterization by PARC systems, I'm going to send in a third link, and you can reach us at parcafm.com. That's again parcafm as in atomic force microscopy.com, and you can use the contact us button to reach us or any of our partners around the world to get in touch with you with how we can best enable your nanoscale advances. I see that we don't have any other questions in queue, so with that said, I think we are probably set to close. Do you have any final thoughts for us today, Professor?
Yeah, well, again, I'd like to thank you, the audience, and I hope you've enjoyed this webinar series and have found them useful for your education, your knowledge of this area, nano research, chemistry, polymer science, etc. So watch out for our future programming, and I'll be happy to correspond with the rest of you. Thank you.
All right, thank you very much. And one last parting link, the link to the archive on parcafm.com, the Nano Academy collection of presentations by Professor Advincula, as well as several other speakers that we've conducted in the past year. Again, parcafm.com. With that, I'd like to thank you all for joining us this morning, afternoon, this evening, and we hope to see you again in the future. Take care, everybody, and have a good day.
Bye.